Welcome, everybody. This is our second live stream for the zkVerify Hackathon, and that's open for registration right now. It's for all ZK developers to come develop with whatever type of ZK proof that you want, small, useful applications. There'll be a link on, well, there's lots of links we'll share. So I want to introduce our two presenters today. We got Marco, who is product marketing at zkVerify. He recently judged at the hackathon at ETH Rome, presented at ETH Sofia, and is just returning from DevCon Bangkok, where he went to, I think it's like 10 or 15 ZK focused side events. So he's got all the latest scoop. Steve is QA developer at zkVerify. He is a hobby hacker, loves to just develop things on his own, got into Bitcoin in 2013, has been a developer for almost 2 decades now, and was recently at ZK Hack Montreal, at ETH Sofia, at ETH Warsaw. So a lot of good recent hackathon experience. So these are the types of guys that are involved as judges and people to help you out on the hackathon. Marco's going to do a presentation on, and we're going to make it an interactive presentation on the zkVerify architecture, and then Steve's going to go through some of the basic developer tools. So in this series of live streams, we're going to progress from the very beginning as introduction to late next week, very detailed technical ones. So we'll build up a library of videos for everyone to share. So before we start, Marco, Steve, do you have anything that I might have forgotten or that you wanted to share before we start? This is a pretty straightforward, how we do things. Marco, go ahead.
Well, not really. Just have to say that I'm super happy to be here and to go through the zkVerify architecture and hopefully provide some great information for all the hackers out there.
Nice. Steve, before we go?
Yeah, just excited to show everyone the tools that we've developed to make developers' lives easier. So you'll see some of that after Marco's presentation.
Awesome. All right, well, let's get rolling.
Okay, so let's go. Today, speaking about zkVerify and specifically about its architecture, and thank you all for the presentation, and let's dive in. So before going into zkVerify technical details, I would like to go through a little refresh about ZK proofs, what they are and how they work. So in a nutshell, in a ZK system, we have two main actors. We have the prover and we have the verifier. For a certain kind of ZK proofs, we also have a trusted setup that is necessary for setting up the system, and this applies only for ZK snarks. The way it works is that we have multiple entities and a random number that is the one-time secret string needed to set up the entire ZK system. And this process has to be conducted in a very careful way, because doing it wrong means breaking the cryptography. So it's a kind of a trust assumption, and this applies only in ZK snarks. And where this applies, we have some parameters that are distributed to the prover and the verifier. But going back to the main actors, the prover and the verifiers, we have some inputs that are given to both of them. For the prover, we have the private input, that is the secret that we want to keep private and not to share with anyone else. And oftentimes it's called a witness, and it's basically what we would like to prove some claim, some statement upon. And apart from that, we also have public inputs that are the public inputs used for performing the computations, and these are distributed to both, to the prover and the verifier. So how the system works, we have the prover with the private and the public input, generating a proof, sending the proof to the verifier, and the verifier verifying the proof. And this finds application in a lot of different use cases. And if you want to go through a practical example, we can consider like the whole life cycle of a zero-knowledge proof, bringing what I said before to to a blockchain-related example. So on the left, we have a few zk apps on the Ethereum blockchain. And if we take as instance the zk app number 3, we have the zk app with its own business logic in the smart contracts. And at a certain point, it will generate a proof upon certain inputs, certain computations. And we have the prover generating a proof, P3, here in the diagram. And then the proof is verified on Ethereum through a verification algorithm. And at this point, the zk app goes and retrieves the verification result from the blockchain. Very
So, Marco,
straightforward.
let me jump in here because we've been talking to different people doing zk proofs and verifications all year long. And at the beginning of the year, the mindset, as far as I could tell, was that everything needed to be verified on Ethereum or an EVM using the precompiles on the BN254 curve. And there's been that started back in 2017. There's been so much research on zk proofs since then. But I think the big thing that the team at zkVerify figured out well over a year ago was that everything is funneled into being verified on an Ethereum or an EVM. And there's a lot more different types of zk proofs out there than just like the Gross 16 or Halo 2, right?
Oh yes, that's correct. Like we are seeing a lot of different proof schemes being researched in the academic environment and then applied immediately after in the real world, specifically in the blockchain space. And because of that, it's oftentimes difficult to write to implement those kind of proof schemes in smart contracts, real world applications.
And that reminds me, Steve, when you were at hackathons, I remember you telling me that people are working to use with zk virtual machines, and those, from what I can tell, they'll take Rust code and they'll verify that it ran correctly, and then they'll generate a zk proof of that, and it's generated as a Stark, but then it's wrapped into something that can be verified on Ethereum. But we can verify the intermediate proof, right? And were the hackers that you talked to, do they like the idea of being able to not have to put everything into the Gross 16 or Halo 2 on that curve?
Absolutely. So obviously these zk VMs like Risk Zero, and we've got tools now from Noir, things like their Ultraplonk. These are all designed to abstract away a lot of the complexity that you would see in lower level circuits. If you were using something like Circom, they're providing a layer on top that makes it a lot easier for even for non-ZK devs really to get started. So with people using these tools, obviously there needs to be a way to be able to publicly verify them, and that's obviously a solution now that we provide.
Nice, yeah. That Marco, your slide here, it made me remember that we need the proof created and it needs to be verified, because it doesn't do any good to create the proof with fancy new zk technology and then not verify it. But so that anyway, that's why we talk about the verification side. Sorry to interrupt. If you could continue, that'd be great.
Yeah, exactly. And related to what you just said, Rolf, like we also realized that the modular narrative we have seen picking up in the last couple of years can be applied to basically every part of the blockchain stack, and also to zk proof verification. And a modular life cycle of a zero knowledge proof will look like it follows. So we have the same setup as before with the different zk apps, but instead of sending the proof natively on Ethereum for verification, it goes through a dedicated proof verification layer. And the reason for that is that, the verification layer can be dedicated, and because of that, be faster and cheaper for verification. And
Hey, those are key words though, because every time I talk to people about zk stuff, they're like, "Oh, it's for infrastructure and it's slow and it's expensive." But if we do it this way, like you said, we can have the proofs generated quickly and inexpensively and verified quickly and inexpensively. And that way it expands from beyond infrastructure to just basic applications, maybe just individual user apps like games, right?
Yep, that's correct indeed. And I think that the two key questions here are why we should modularize and why having a dedicated verification layer for that. Well, I think the reason is quite obvious because verification costs are pretty high. And here on the right, you can see a table with different proof types and associated gas cost for verifying the proofs natively on Ethereum. And apart from that, there is also a projection of how much it will cost in terms of USD, considering 7.5 Gwei and Ethereum at 3K. And we can see that verifying a single proof, going from the most simple ones like Flonk to more complex one like Stark, ranging for $4 to more than $50. And this is definitely an issue for the widespread adoption and democratization of ZK technology.
So on this slide, when I was in a previous industry, the IT field, we always said that price is always part of the design factor. And there's a lot of different applications and ideas that people have built regarding using ZK proofs, whether it's for private polling or private messaging or proving that something is true on a Web 2 application. But if it costs you $5 to generate a proof and $5 to verify a proof, nobody's going to do private polling or private voting. Now, earlier this year, did talk to some of the ZK coprocessor and zkVM organizations, and they say that some people design to have their proofs verified on an EVM, like Optimism or Arbitrum, and then use message passing on Wormhole to get the verification done. So there's already people in the space that are designing to have their proofs verified on the least expensive place possible and then send the message passing. But it still runs into it has to be fitted onto the BN254 curve. And so we already saw at zkVerify that there's people that just want their proofs verified publicly. So I'm eager to hear what you have to say about how zkVerify is going to address this.
Yeah, no, that's right. And also another consideration, like coming back from DevCon, is that people, they want to verify proof, they want to verify them publicly, but also they want the verification result to be on Ethereum because Ethereum is the most secure and decentralized chain out there. So it's also a matter of trust and to rely on the, I would say the more trusted, trustless, decentralized chain. So
well, that was in the Web3 space, right? So one of the things, Steve, that you told me when you came back from ZK Hack was you were surprised how a lot of the people that were developing apps on ZK proofs, they just needed a public place, a decentralized blockchain to get the proof verified. It didn't need to involve a smart contract. Wasn't there a guy that did something with Telegram and zkVerify? Can you talk for a minute about that?
Now I have to remember exactly what this guy did. Yeah, I think I'm trying to.
It was the Z-gate that was gating the chat, right?
Yeah, it was gated. It was gated chat, wasn't it? It was some kind of proof that that you were allowed to join a Telegram group. Of course, that could be anything. If you were to associate it with crypto, for instance, you could say only individuals with a certain net worth in terms of crypto could join, or so a whale group, for instance, or an NFT community, prove that you have something without revealing exactly what NFT you have or how much money you have. So that's the kind of what we've seen previously. But yeah, also it doesn't necessarily have to be I mean, that's obviously an example of not necessarily using a Web3 app, using a message service or using any other kind of Web2 based application, people proving databases and all that kind of stuff at the moment.
Yeah. So
I think your original question, like, do you have to prove it on a contract? Not necessarily. It's having that different way of doing it, isn't it? At the moment, these proof verification costs are because we have essentially Solidity code and contract code that's increasing the cost of a transaction in order to perform that verification. So that's the part that we're kind of moving off chain or off the main chain, and kind of obviously doing that ourselves, and also providing a way to verify what we're doing can be trusted.
Okay, cool. Throwing it back to you, Marco.
Okay, so before moving to the next slide, I think that another, like the last takeaway from this one is that the verification cost is very high because the EVM is not made for verification, like for doing this kind of cryptographic computation. So it lacks natively the precompiles, and that's why it costs a lot in terms of gas. And we have like sourced some publicly available data, and realized that since a few years until now, the total spent for verification on Ethereum main chain has been more than $60 million from ZK apps, roll-ups, basically any kind of application that relies on ZK technology and verifies on Ethereum.
Yeah, because so this is, I think it's mostly ZK rollups, although I think WorldCoin adds a lot to this as well. They do a lot of verifications. I think they moved to Optimism or their own chain for that. But this is the appetite for applications that can afford to spend $5 per verification and take 5 to 20 minutes to, or whatever the variable time to get the proof verified is. So to me, that's just, if the ZK application space is this big, the ones that can afford $5 per proof verification is this small. I bet there's a ton of other use cases that are looking for a lower price way to create the proof and verify the proof.
Yep, correct. But things can be different. And that's why we're working on zkVerify, which is a dedicated zero-knowledge proof verification layer. And it's a layer 1 modular substrate-based blockchain. And it's designed with two goals in mind: provide consensus and verifying proofs by consensus. And if you want to have a brief look of zkVerify architecture, we can see a proof generating system, basically the ZK app we had in the previous diagram, sending a proof along with some public inputs to the zkVerify network. And the network verifies the proof and store it through some native verifiers, depending on the proof scheme, Flong, Groth16, RISC-0, but also more. And then the verification result is sent to the zkVerify smart contract on Ethereum, and the smart contract from the application goes to retrieve the verification result, update its status, and then execute its business logic, and goes on with its own DApp operations. If you want to take a look about zkVerify nodes, how they work, and why they are so efficient, we can see a brief chart over here. And we can see that the zkVerify node is divided between two different sub-components. We have the node client and we have the runtime. The node client is the part that takes care of everything like networking, consensus, storage, and so on, while the runtime is like you can see the little rectangles in here that are called pallets and are plug and play modules that offer some additional capabilities to the chain. So we have some pallets for security, like the staking pallet, we have the multisig pallet, we have some pallets about governance, like the referenda, the treasury. But I think the most important one here for what we are trying to explore is the one about the ZK verifiers. And zkVerify implement one different pallet for each proof scheme that we currently support, with more support for other proof schemes coming very soon. As soon as new proof schemes are developed, zkVerify can implement this new pallet in a very easy and seamless way without requiring any hard fork. And as of today, zkVerify supports all the palettes for verification you see here. So we support Flonk from the Polygon CDK. It supports UltraPlonk for Noir, developed by Aztec, the zkSync era that is based on volume proofs, but also Groth16 and Starks from the RISC-0 zkVM. Last but not least, we have the proof of SQL for space and time that is doing zero-knowledge access to databases.
So, Marco, I know that I agree. The verifiers here are really important, and we got 4 more in the pipeline that that partners are developing for us. However, I was having a conversation with someone yesterday, and they're saying, "Well, how we say it's a decentralized system, but and that's important to people. But what are the details of the decentralization?" And you've got that in some of the other palettes and or modules here. Substrate is a very well developed and used blockchain technology. Of course, it's what Polygon and Kusama runs on. There's a huge open source community that contributes to it, so very secure. The system that's set up in sending the proof to be verified, once 2 of 3 validator nodes verify it, then it gets put onto the blockchain, and the blockchain has a 6-second time. So as soon as it's on the blockchain, anybody can, with regular blockchain type tools, whether a block explorer and Steve's going to talk about those tools in a little bit, to see that the proof was verified. And then, like you said earlier, Marco, it can be sent to a zkVerify smart contract on a smart contracting blockchain. And right now we're connected to the Ethereum Sepolia, the 8-chain Curtis, and the Horizon Eon testnet. So I think all these are really important because people want to have their proofs verified in a reliable, secure, decentralized, permissionless blockchain quickly and at low price. And all these things contribute to that.
Yep. No, it's very important that the verification happens like the verification is baked into the consensus and performed by the validators in a decentralized way. And in this way, the verification result cannot be tampered with like it would happen with a centralized server.
Hey, so I don't know if y'all know, but there are, for the people that are watching this on live stream on X, you can type in comments and those show up here for us to answer. So we got a question here, and I'm going to briefly step away from this presentation. We'll come back to it, and I think I can actually post this question here. Okay, so the zkVerify smart contract on Ethereum receives only the verification result from the zkVerify network, and there's no verification happening there. That's exactly right. So, Steve or Marco, correct me if I don't get this quite right, but the way that it happens is the proof is sent to zkVerify, a digest is created of that proof. The proof is verified. The verification is put into the block on the blockchain. And then every 100 or so, it's either based on number or time, the hashes of the verification are put into a Merkle tree. That Merkle tree root is sent through either a centralized bot, which is very quick and deterministic, or a decentralized bridge. And our team is building the connection to the Hyperbridge, one of our sponsors for this hackathon. And that goes to the zkVerify smart contract on Ethereum Sepolia or 8-chain Curtis. Steve, can you talk for a minute on how people can then see that verification was done in their smart contract on that EVM? And I know you get more into detail later, but if you just have a high level of it.
Sure, yeah. Like you said, we raise, I guess, what would be called an attestation event on the zkVerify chain. That happens after a certain number of proofs or a certain number of seconds, whichever one comes first. A bot picks that up. It will post that to our contracts, our zkVerify contracts on the various EVMs. That contract provides a method for you to provide the inputs for your original proof and verify that it does exist as part of that attestation.
Cool. Thanks. Oh, that's really helpful. All right. Yeah, appreciate the questions. And Mark, I'm going to let you continue.
Okay, thank you, Rolf. So going on, the current slide is just a summary of all the proof schemes that we've seen before, and that it's a developer choice to choose the right proof scheme, the most suitable one for their application. So it really depends on what you are developing, what your use case, and what kind of proof scheme you want to support for the application. We have different, as we have seen before, trust assumptions and trade-offs between different proof schemes, specifically Snark and Starks, but at the end, it really depends on the specific application use case. And just concluding very briefly with the zkVerify, going all this through modular and decentralized process, the cost saving is projected to be more than 90%, and so zkVerify can actually reduce that cost by, I will say, quite a lot. And on the right, on the fourth column, you can see the projection for the cost saving and the final price for the verification of a single proof with zkVerify. So we can definitely bring down the cost by more than 90% and have proofs verified for the fraction of $1. And yeah, I think it's quite important to develop this kind of service for the wider community and Ethereum ecosystem, and to be able to have zk tech adopted and employed by as many apps there are out there that actually needs to use zk for privacy or scalability purposes.
Yeah, and then on our last live stream had product manager John Camardo talking on here. He said the more than 90% is key, because these are just our projections right now. I know that the technical team has done some optimization recently by moving some of the primitives from the runtime into the base verification. So it's entirely possible that we might be able to reduce the cost of these proofs by another order of magnitude or even more. So we have projections and we have good ideas on how this is going to work. Obviously, this is a blockchain. It is not only decentralized, but it is going to be owned by a foundation, a DAO. The people that are going to be owning the tokens are going to be voting. It has a way to have sustainability, so people are going to pay for the proof verifications with our zkVerify token. So this is going to be a whole working system. So this is our projection for the beginning. It may be that we can reduce these even more. And I just realized that didn't fully answer the question that came in on x.com. So the proof, and this is a little tricky, so we might have to save the full answer for this until we get Daniela on here next week. But my understanding is that the proof is stored for a short period of time in non-block space on the validators. The zk proof is not stored itself long-term on zkVerify. A digest of the proof is stored. Of course, we listen to what the people that use our system want. If it turns out that storing the proof long-term is something that is useful, the really cool thing about Substrate and zkVerify is zkVerify is set up as a relay chain on Substrate. Not a lot of Substrate relay chains out there. So we can actually add parachains, and it may be that we add a data availability parachain to store the proofs that are submitted at an additional cost on a parachain. So there's a lot of design options that we have here. Yeah, go ahead, Marco.
No, I'm super excited about zkVerify being a relay chain, and also about being able to add more parachains. Depending on what we're going to see in the future and how the space is going to evolve. But yeah, just to conclude, I will now pass the mic to my colleague Steve for an hands-on session on developer tools. So,
Thanks, Marco. That was great.
Right, let me just share my screen.
Yeah, as Steve's getting ready here, so Steve's been involved in face-to-face with a lot of the people that are working to develop on zkVerify. So if you go onto the Devfolio link, you'll see that under the frequently asked questions. And Steve, just pop your thing, your screen up here backstage, and I'll add you as soon as you're ready. So on the frequently asked questions, there's links to previous hackathons where people designed with zkVerify. There's also links to example applications that we have in the Horizon Labs GitHub. So Horizon Labs is a gold sponsor for this zkVerify, and Horizon Labs, of course, this is part of the team that originally was did the developing and marketing for Horizon. Horizon started out as Zencash. I was co-founder of Zencash way back in 2017. So Zen is going to get a lot of the benefits of what we're doing here on zkVerify as Zen goes through a big upgrade here over the next few months as well. So stay tuned for that. Steve, let me know when you're ready. I see that your screen is showing the three of us. So I'm not sure I want to share that screen because we're going to
I'm sharing my whole screen. I just waiting to unmute myself once we're ready.
Okay, I'm ready.
All right, let's go. Let's do it.
Okay.
Let me do. Let's get this a bit bigger. Let's start off right at the beginning then. So we want to have a look at some of the developer resources and tools that are available to you guys to get started for the hackathon. So first point to look at is to go to our website, zkverify.io, and you will see the start building link, which is going to take you to some of the pages I'm about to show you now. So one of the important ones in our documentation is the zkVerify hub. This contains a lot of the links to the explorers, faucets, and wallets, and also our deployed contracts on the various EVM testnets. So please check that out and get familiar with everything that we've got there. So we'll start with supported wallets on Substrate. I think the wallets that we're recommending at the moment are Subwallet and Talisman. Both of which I think have Chrome extensions and phone apps to use. And then on to the next point then, for anyone starting on our network, is to use our faucet and get some testnet funds that will pay for your proof verifications on testnet. So again, all these links exist already. Just double check. Let's see this working. So I'm just going to copy this. It should be nice and simple. There are some checks as you would expect with a faucet, so no one can go crazy and drain it. But yeah, as you can see, that's pretty quick. I'll have some additional funds.
Steve, I tried to get some and it said I had too much in my wallet already. It wouldn't let me get any more.
You're a wealthy man, Rolf.
Yes, I can share testnet zkVerify with anybody that needs it, for sure, if they need more than what you can get from the faucet.
Yeah, so, well, I mean, I think we're giving out a generous amount from the faucet at the moment on testnet. That should last anyone a long time. But yeah, absolutely feel free to reach out on Discord, and we will get some more sent over to you if needed, if you're a heavy user. So on to the next one. This is one of our newest block explorer. So again, most people here should be familiar with a block explorer, and this will allow you, like all the others, to view blocks, view the proofs that have been sent in, view transfers, and all that kind of stuff. So in Substrate, a lot of the external actions that you would perform are essentially called extrinsics. Anything where you want to write or read data will be in the form of an extrinsic that calls a palette, and palettes on Substrate are essentially modules containing their own functionality. So that's the nice thing about Substrate. You can avoid all the bloats and pick only the palettes that you want, and then also obviously develop your own palettes and functionality for your chain. So yeah, Block Explorer, everyone's seen it. You can see things like the palettes that we support with things like RISC-0 and the inputs that we used for that particular proof. So maybe coming back to what you were saying previously, Rolf, obviously you can see here that with a Block Explorer indexing the transactions that are coming in, that we do actually have the data to be able to send this again. So in effect is storing the proof itself. We have a proofs dashboard, which is steadily climbing. You can see everything that we support, although it does look like we're missing some actually. But we'll go back to make sure that we've added in everything that we currently support. Moving on then to Polkadot.js, which is essentially a UI that allows you to connect your wallet and interact with a blockchain rather than doing it through code. So you can go to the developer tab and the extrinsics. You can pick what palette you want to interact with, pass in the data required for that palette. So for instance, for this one, you might, if you want to submit your proof, you can do it all through here. Obviously, this is a very slow manual way of doing things, but can be used in that way in certain scenarios. Okay, so I'll move on then to the npm package that we have, and then some demonstration code here. So obviously, a lot of the code and the functionality that we've implemented is complex, and we've created a JavaScript package that tries to abstract away a lot of that complexity and provide easy to use functions for connecting to our network, querying our network, and obviously the verification of all of the proofs that we support. Maybe I'll go into this in a little bit more detail. Sorry.
I'm pretty sure you wrote this, right? And then you've been improving it?
That's right, yeah. So this was, as one of the first users, I guess, of zkVerify, it was it became as with anything, it becomes quite obvious where some improvements needed for the developer experience. So that's what this was born out of, and obviously developer feedback is always appreciated. Obviously, this is designed to work for the developer and make it quick and easy to use.
And you're on like the 4th or 5th improvement of this. What are some of the recent improvements that you've made on this?
Recent improvements on this. So I guess the very latest one was purely documentation changes. We've tried very hard to make sure that our documentation is very thorough, very clear. So absolutely would like feedback for that. But then what you will find with additional releases, or the ones just before that, would be things like utility functions, being able to format your proof or create the extrinsic separately from the process of actually sending it to the blockchain. And obviously, each time we add a new verifier, we have to support that within this zkVerify JS package as well. So the very latest one was space and time, which I think was 0.30.
Thanks.
Okay, so that's a little bit of a giveaway there on that page. So essentially, that's a very brief description of our npm package. I will give you some examples now of how this is used. So one of the things that we have created, let's see if I can increase the size of this. Oh, is it? Okay, let's ignore that for now. That should be big enough. Okay, so one of the things that we do have is essentially an npx command that anyone should be able to run, or as long as they have Node installed on the machine. You should be able to run this command, which is designed to bootstrap a new zkVerify Next.js project. As you can see there, this is using Next.js 14. So you can see down here what I've done is the actual npx command itself is here, and I'm specifying a name for my project, which is going to create a new folder within this demos directory and begin to install everything that we need. So I'll just run this. It does take a little bit of time. Of course, I have one pre-prepared. But yeah, this is pulling everything down, creating a new folder, as you can see, and trying to get everything you need set up to get up and running. And what we'll do, we'll switch over into the pre-existing one, where nothing in here whatsoever, but we can cd into here, zk projects. Actually, let's just double check. Does that go? Right. Let's go over. Okay, so simple commands, as most people who are used to JavaScript or running a website, npm run dev, all of that information is in the package.json scripts. But essentially what we've done here then, we've pulled down our Bootstrap projects. Everything has been built as part of that command. We're just running it using the dev command, and that's now running on localhost. So what we're going to see on localhost, just let this refresh. So this is a very simple web app that just has a connect wallet button and is going to submit a hard-coded proof. We'll take a look at the code after this just to see what it's doing. So we've got some example code then for connection of the wallet. I've got 2 wallets installed. I'm just going to pick one. And then the ability to submit a proof. So when I click this submit, obviously as with any transaction, I have to sign off on it and approve it. This is now submitting to zkVerify and listening to events. And again, we'll take a look at the code in a second as to exactly what this is doing. But essentially, we've got a JSON file with the fields required for risk 0 to be able to verify that proof, and we're submitting it to zkVerify. So the outputs here, obviously you can see we've got a transaction hash for its inclusion in a block, the proof type, and the attestation ID that's been assigned to that proof. You can then also view this on the Explorer. So I think actually my code for this example is still pointing to our old one. But what we can do is go back to here, search for the block. It says, you can see here. So this is the one 1 minute ago that we've just submitted. We can click in then and view everything that we sent. So that was successful. That's been verified. We've got an attestation ID. If we chose to, that would then be sent to our target EVM and can then be verified using the zkVerify contract. So if we switch back over to the code, in fact, let's have a look at the other install. So you can see the previous installs now completed, less than 60 seconds, and exactly how to run the commands I just showed you down at the bottom. So if we take a look at in terms of what we're doing then, in the source folder, we have the main layout file that's being wrapped in an account provider, essentially all the code that you need to be able to connect your wallet and have the connected wallet state across your application. Some very simple code on there just around showing the result and setting the results of the verification, and the main integration. Sorry, let's go back here. So we have a connect wallet button. Again, this is all code that you guys can use straight out of the box. Provides all the connect wallet details that you need for using the Talisman npm package, which will allow you to connect with Subwallet, Talisman, and all the other ones that are supported. Now, the main code for our integration here is the use zkVerify hook. And this is essentially importing lazy importing the zkVerify.js package, connecting to our testnet. So again, this is all within our documentation, but you can see to start a session with zkVerify, we're just providing what we're connecting with and that we're connecting with a web wallet, basically. So anything that's connected with a Chrome extension or app wallet will be found here. And then what we're doing, we're passing in the proof data from the RISC-0 proof and sending it to zkVerify, and we're awaiting the events and the transaction results. So actually we're listening for the events, which is allowing us to provide real-time updates on the UI as to how it's progressing through the chain. So you're included in block, finalized, rejected, failures, all that kind of stuff. And obviously messages if your proof was invalid or failed verification. So this is reading in from a hard-coded proof file. So actually, as part of this Bootstrap project, we've got some example proofs for everything we support, apart from space and time at the moment, but that's something we will add in very shortly. But what this is doing is this is just pulling out the data required from for RISC-0 in terms of the verification key, the public signals, and the proof, and just allowing anyone to get up and running very quickly. So if you purely just want to test the integration with zkVerify and you've not got a proof or anything yet, you can pull down this project, bootstrap the project with the npx command, and instantly send this RISC-0 proof. But you can also change out this within the code if you want, and obviously try out the other proof types like Groff16 or the UltraPlonk. Have we got any other questions so far?
We don't have questions. I think people are just like me, entranced by seeing all the work that you've gone into and how you do this. This is what we've needed for people to be able to develop. I'm so excited that you're doing this, Steve. Please continue.
I'm glad. Right. So, I mean, there's probably not too much left here. One thing, obviously, that this is doing is providing a button on the UI to connect a user's wallet, and they pay for it. The other option on this, which I guess we can go through the zkVerify docs a little bit. One of the things that we do have is the ability to connect either with a wallet or with an account. So if you're a front-end web app application and you want users to connect to wallet and pay for the verification, you will use the with wallet command and set the relevant sources for the wallets that your users connected. Or you can choose to use with account, which essentially would mean that you provide a secret seed phrase. So obviously that would be stored securely and passed in as a secure environment and variable, but you would pass that in using the with account. So let's have a quick look at actually starting off with zkVerify JS then. So as we saw in the code, there is the actual starting of the session to connect to zkVerify. We have the pre-configured testnet, and we have the ability to set a custom network. So this would be used if you are running your own node and you don't want to use the RPC network. You would specify exactly where your node is there. So if you're running one locally, you can use localhost, etc. We can see here the use of the with account and passing in the seed phrase, which would essentially mean the app or the app developer or the app is paying for the cost of verification as it happens, or the with wallet. You can also decide to start zkVerify JS in a read-only session, which essentially is only giving you access to its read-only methods. You're not able to transact, essentially, and would be blocked from doing so. The verification steps then can be seen here. Once you've started a session, you then have access to being able to specify the proof type, whether you want to specify a nonce, that's optional. You can set it. So I guess the nonce would be set if you were parallelizing your transactions, for instance, and there was a chance that this value would get confused by trying to pull it down each time from the chain. The option to wait for an attestation to be published. So this is what we spoke about earlier, whereby an attestation is published after a certain number of proofs have been created or a certain number of blocks have been created, whichever comes first. The option to use a registered verification key. So this is one of the things that zkVerify provides. You can register a verification key. For instance, they can be quite large and get back a hash value that points to that verification key. So if you are verifying proofs or the same proof over and over, that becomes very important. And then the actual execution step at the end, which is passing in the actual data. You're able here to either pass in the original verification key or its hash. If you've specified with registered VK, it expects this value to be the hashed value returned from zkVerify. Okay, let's have a look, see what else we have. I think we've probably talked about some of this stuff. So we've got sections here that go around how you would actually go around registering the verification key. Also very important for blockchains is the events. So as we saw in the code, the ability to listen to everything that's going on once you've submitted a transaction. So as it gets through the various stages of inclusion, finalization, attestations, and errors, you can listen to all of those and handle them appropriately in your own code. And then finally awaiting a final transaction result and being able to use that transaction data straight away in your code then.
Steve, I got to say, this is beautiful documentation. I mean, I'm always, I'm always talking about us having good documentation for developers because there's so many smart people out there that can figure things out, but they need good documentation that shows how to use the application. So I just want to say I'm amazed. This is awesome documentation. So don't let me interrupt you, but I was thinking about that as you're going through this. So I know I appreciate it. I'm sure a bunch of other developers do as well.
Absolutely. Obviously, we all know documentation is important, and too often it's ignored, or we say it's going to be done at a later date, and it never gets done. So we made that a priority as part of this to ensure it's fully documented, and we can update it if anyone wants to raise any issues or anything's unclear. Obviously, this is designed to make things very clear and easy for everyone. Okay, so other options on there, you can wait for the published attestation. So waiting for a published attestation means that you're waiting a bit longer for the transaction result to be returned. Although the transaction would have been finalized, the attestation event wouldn't be raised until a bit later. So if you really need that, you can use it. Otherwise, if you want something quicker or some kind of, which you can also get from the events, I guess, but if you want to ignore that, you can. That's an optional value. I think this is just a large example again here of a full script of how you would send the transaction to send your proof to zkVerify, listen to all the events, handle any errors. And then we've got at the bottom of the documentation a full API reference for everything that we provide for within zkVerify JS. I guess some of the important ones would be that we haven't touched on would be the proof of existence, which is essentially passing in some of the data that you would have had returned back from your initial verification transaction, and then being able to prove that it does actually exist at a later date. This was a recent addition, although we did it internally anyway. This provides essentially a way for you to pass in the raw proof data from the various projects that we support and format it in a way that zkVerify accepts. So you can go through that and view exactly how it's done if you need to. I think I've touched on this at the very beginning, creating a proof extrinsic and being able to utilize it later, turning it into hex value, estimating the cost of your proof verification, getting things like your account information on things like your balance and current nonce, subscribing to events, so not just your own. You could subscribe to all events if you want to, if you wanted to run some kind of indexing service or something like that. This provides all that functionality. You've then also got the direct access to Polkadot.js, which a lot of our package uses under the hood. So if you need to use the API directly, you're more than welcome to. And I've just seen that we're towards the end, but that's pretty much it for my overview. I hope I didn't take too long.
No, I would have been happy for you to go another half an hour doing this kind of stuff. So appreciate it, Steve. Yeah, on this kind of stuff, where we're rolling, we got as much time as we want. Now, we do have a question, but before I answer this question, I want to say that earlier, as we discussed, we're going through a technical progression as we go. So our first video, fairly non-technical people, John and I. So now we've got Marco and Steve talking about the developer tools. Next week, on Monday, we've got another session where we talk about some example applications. So one of the things that we're really doing well with is we're working with ApeChain, and as you saw earlier, Steve, you pointed out that we're integrated with the ApeChain Curtis testnet. So there are some games and game developers that are integrating zkVerify for things on ApeChain. One of them is provable randomness. There's a few other things there. We have some examples of how to use zkVerify in code, and we're going to go over that on Monday next week. One of the hackathons, a winner of a zkVerify prize, took a zk Mastermind game and created that, or not created it, but modified it to use zkVerify. So we'll go through that. There's a Sudoku game that uses zkVerify, and one of our other sponsors, Sindri's system. So we'll go through that as well. Now, I'm going to attempt to answer this question, but it might have to wait until our Wednesday live stream, and that's where we're bringing in the ZK big guns. So we've got cryptographers, we've got developers that for many years have been integrating advanced ZK cryptography into code. And so the question is, and I'll pop it up here. I know this is one of our hackathon people that have already done the hackathon, joined the hackathon. Can we do recursion? So now I'll explain what I think recursion is, and then we can talk about whether we can do recursion using a verification key or not. To me, recursion is that you take information, you create a ZK proof about it, and then I believe this is used in quite a bit when you want to have a continuous stream of things that you prove, so you can just kind of add on the ZK proofs to the previous ZK proofs. So using a verification key, this would seem that you can refer to previous proofs that have been verified. So I'm not sure it would be as strict type of recursion as other types of recursive activity that are done in the ZK proof space, but it may be a more basic version of recursion. I don't know. What do y'all think? Do we need to wait until we get the cryptographers on here next week? I think so too. All right. We're not going to even try to tackle it, but go ahead, Steve.
Yeah, I think there's just we need a little bit more clarity on that question. I think.
No worries.
Even our devs just need a little bit more clarity. So that's
yeah. And so, but that's a great point, because the people that have joined the hackathon already, some certainly on our Discord, we have a hackathon channel on our Telegram group. People can ask questions publicly, and of course our devs monitor those and jump in. If there's very specific questions that people would prefer to do privately, we want people to succeed in this hackathon. So for obviously technical folks that have detailed questions like this, happy to set up small Discord groups, small Telegram chats, and help y'all work through. Now, reserve the right that we take some of these questions, generalize them, and put them in our frequently asked questions section to help everybody else. But we're not going to give away what your project is. So I think that's good for today. Marco, really enjoyed your presentation, doing the overview of the architecture. Steve, really appreciate you stepping through the different tools that people can use to develop applications for zkVerify. Give you all the opportunity for last words here, and then we'll wrap up. Hop in if you got anything that jumps to mind or you want to say, and if not, we can just end.
Yeah, I have to say, just super excited about the hackathon and all the different submission and application we're going to see. And thank you all for being such a lovely co-host. Really appreciate that.
Thanks, Marco. And Steve, I think we're going to have you back on another one of these, but go ahead.
Yeah, that's my my first live stream, which I've survived. So that's always a good thing.
Dude, you crushed it. I mean, that was awesome. We're going to be taking clips of this recorded video, and it's going to be showing up everywhere.
Don't turn me into a meme. That's my my fear. Don't be some random snapshot of an awkward position.
There's worse fates in the world. All righty. Thanks, y'all. I'm going to end this stream.
So that, guys.
Thank you all. Bye.